whispering the threads converge. From just a single point of inquiry way back in 5th century India, this whole cosmic picture has been built up. We've followed it all the way, haven't we? From that initial idea to understanding a spherical Earth spinning in space, how its rotation sets our daily rhythm, how shadows tell us about eclipses, and, well, this idea that knowledge is something precious, something to find and protect. What does it all tell us, this unified vision? About the cosmos, about us, about just the power of asking questions.
It's quite something watching this entire structure emerge from one text, the Golapāda. It's not just, a list of observations. It's all connected. Each idea supports the next.
Welcome back, everyone, to Ancient Code, Modern Mind. And yeah, this is more than just wrapping up one segment. It feels like the end of a whole journey. Over the last 10 explorations, we've really gone deep into the Golapāda IV, the final book of Aryabhata's Aryabhatiya, the chapter on the sphere.
The grand synthesis, really.
Exactly. It's where all the math, the trigonometry, the time cycles we've talked about, it all comes together into this, well, revolutionary model of the cosmos. So today, we're pulling all those threads together. We've got guides like Bhaskara helping us see the finer points. We want to really get a feel for the scale of this achievement, the audacity of some of these ideas, and how they still echo today, ready to align these spheres.
Absolutely. And, thinking about the context of the Gupta period, it was a time ripe for this kind of thinking. There was a definite move toward looking at the world, measuring it, reasoning about it. Aryabhata was right at the forefront of that.
A real intellectual shift.
Definitely. And the Golapāda embodies that. It offers explanations based on geometry, on observation, moving beyond just the traditional myths or stories. It grounds astronomy and mathematics.
Okay, fellow seekers, welcome back to Ancient Code, Modern Mind. Today really is the grand finale for our deep dive into Aryabhata's Golapāda, and actually for this whole season looking at the Aryabhatiya. We started way back thinking about this key text from the Gupta era.
Episode 25, wasn't it?
That's right. And from there, we've seen this entire astronomical system unfold piece by piece. It's clear Aryabhata wasn't just collecting facts. He was building a working model of the universe, verse by careful verse. And the Golapāda is where it all takes its final spherical shape. So let's start right at the beginning. The canvas for everything. The celestial sphere, the Khagola.
The apparent sphere of stars, yeah.
We talked about how he saw this sphere seemingly rotating around us, and within that, he mapped out the sun's path, the ecliptic, the Apamānāla, and crucially, he identified its tilt.
And that tilt is key, isn't it?
Absolutely key, because that simple observation, that tilt, holds the explanation for the seasons, why we have summer, winter, spring, autumn. It's geometry, not just, cycles.
It's a mechanical explanation, almost.
Exactly. And he didn't stop there. He showed how the planets, the moon, they travel along or near the same path, the ecliptic, and he defined their position relative to it using celestial latitude, Vikapa.
So Vikapa tells you how far north or south of the sun's path something is, like its vertical address on that celestial map.
Precisely. It gives you that three-dimensional positioning on this imaginary globe above us.
What's so important about that celestial sphere concept, even though we now know it's not a real shell, is that it gave astronomers a common reference system.
Yeah.
A way to map things, to predict things universally.
A necessary starting point.
Definitely. And Aryabhata defining the ecliptic within it and recognizing its tilt, that was huge. Before him, explanations for seasons were often, well, less scientific. He gave a reason based on geometry. That's a massive leap.
But then came the really big move, placing our own world, Earth, into this picture. Not flat, not static, but a sphere, a Bhūgola, round, made of elements.
And orbiting the center in his model. Geocentric, but still a sphere.
Now imagine trying to sell that idea in the 5th century, people thinking they live on a giant ball. How do you even explain down?
But he had an answer for that. The Kadamba flower analogy, the Kadamba pupamagranthia.
Beautiful analogy. Tell us about it again.
Well, imagine a round Kadamba flower covered in blossoms. Every blossom points outwards from the center, right? But from the perspective of an ant on any single blossom, down is just towards the center of the flower head.
So down isn't some absolute direction in space. It's always towards the center of the sphere you're standing on.
Exactly. It's relative. A brilliant way to tackle that very intuitive objection. And he even cleverly incorporated older ideas like Mount Meru, instead of a huge mountain on a flat Earth.
He repurposed it.
Right. Meru becomes the geographical North Pole on his spherical Earth. Lolka, the corresponding point on the equator directly south. It's about reinterpreting, not just discarding.
That ability to bridge old and new is really something. It's not dismissing tradition, but finding a place for it within a more accurate, more comprehensive model, making the revolutionary seem, well, almost evolutionary.
It's very sophisticated thinking. And that Kadamba analogy is just so elegant. It addresses a fundamental human perception head-on.
Okay, so we have a spherical Earth. But then Aryabhata takes perhaps the most audacious step of all, Earth's axial rotation.
This is the game changer.
He proposed that the daily motion of the stars, the sun, the moon, it's not them moving around us, it's us. Our Earth is spinning eastward on its axis once a day.
And how did he argue for this? Because it flies in the face of direct experience, doesn't it? We don't feel the Earth spinning.
He used the boat analogy. Remember, if you're on a boat moving smoothly down a river,
The trees on the bank look like they're moving backwards.
exactly. So he argued, for us standing on a rotating Earth, the whole stationary celestial sphere appears to be wheeling around us in the opposite direction, westward.
It's a brilliant use of relative motion to explain a perception. But it directly challenged the established view, right? The Prabhu idea.
Oh, absolutely. The idea that a cosmic wind pushed the celestial sphere around a static Earth was dominant. Aryabhata's rotation idea sparked huge debates. Brahmagupta, another major astronomer, initially pushed back hard against it.
But later commentators, like Bhaskar Royer, they defended Aryabhata's view.
They did. They saw the power and elegance of the explanation. It shows this wasn't just accepted overnight. It was a real scientific debate playing out over generations.
Which is how science often progresses, isn't it? Ideas proposed, challenged, defended, refined.
Exactly. And what's fascinating is how Aryabhata didn't just propose rotation, he worked out the consequences. This wasn't just an abstract idea, it had real measurable effects.
Like what?
Time zones, for one. He understood that if the Earth spins, noon happens at different times in different places. He used those cardinal reference cities, Loka, Yamaku, Romaka, Siddhapura, supposedly located 90 degrees apart, to illustrate this difference in local time based on longitude.
So longitude and time are intrinsically linked by rotation.
Precisely. And latitude, too. Your position north or south, your akka, determines what stars you can see and how high they appear in the sky. He explained why observers at the poles see stars circle horizontally, while those at the equator see them rise straight up.
And he gave a method to find your latitude.
Yes. Using a gnomon, just a vertical stick, and measuring its shadow length at noon on the equinox. A direct link between a simple measurement on Earth and your position in the cosmic scheme.
That's incredibly practical. Connecting the grand theory to something you can actually do.
And he even touched on the relativity of perceived cycles. How the length of a day isn't absolute. It would be different if you were standing at the pole, or even, hypothetically, on the moon, depending on its rotation.
Wow. So he's really thinking through the implications deeply. The boat analogy is clever, but connecting rotation to time zones, latitude effects, variable day lengths, that shows a profound grasp of the geometry and its physical consequences. Those reference cities, even if we debate their exact location today, they served as vital conceptual tools for him.
So we have this theoretical model, a spinning spherical Earth within a celestial sphere. But how do you actually use it? How do you measure things in the sky? Aryabhata laid that out too.
Right, moving from the model to practical astronomy.
He defined the observer's local coordinate system, basically how you, standing at your spot on Earth, orient yourself to the heavens. You've got your horizon.
The boundary between Earth and sky.
Your meridian, that imaginary line running north-south directly overhead.
The Dṛkkarma.
And the prime vertical running east-west overhead. The Samantlam. That's your local framework.
Anchoring the observer.
But then he connected this local view to universal coordinates. Things like declination, the apakrama, which is like latitude for stars, measured from the celestial equator, so it's the same no matter where you observe from.
A common language for celestial positions.
And he described the Golapāda, a physical model armillary sphere. You could actually build this device to visualize these circles, these relationships, like an analog computer for the cosmos.
Making the abstract tangible.
And the key mathematical tool, trigonometry. Specifically, his concept of Jaya the half-chord, which is essentially our modern sine function.
The foundation for calculation.
Combine that with the gnomon, the sakku, that simple vertical stick casting a shadow, and suddenly you can quantify the heavens. You can measure angles, calculate positions.
From shadow lengths to celestial arcs. It's ingenious.
And we saw how he applied this, calculating how daylight hours change through the year, the KTJ, explaining why constellations take different amounts of time to rise depending on their position, the Kara calculation.
So predicting the apparent changes caused by Earth's tilt and position.
Yes, and even calculating a star's altitude, how high it is above the horizon, based on the time since it rose. And that elegant method for finding your own latitude, the eclipse, from the noon shadow on the equinox.
That equinox shadow method is just brilliant. It directly links a simple ground measurement to your place on the globe using the sun's known position. It's likely how places like Ujjain, a major center for astronomy, had their latitudes determined so accurately.
It ties the whole system together: observation, geometry, calculation.
Absolutely. These coordinate systems, local and universal, were fundamental. They shifted astronomy towards being a quantitative science. The Gola Yantra helped visualize it, and trigonometry, the Ajaya, provided the engine for precise calculation. It allowed Aryabhata and others to move from just describing what they saw to actually predicting it with mathematical rigor.
But he also knew that observing from the surface of a sphere isn't quite the same as observing from its center, especially for closer objects. And the atmosphere plays tricks too.
Right, the need for corrections, Dṛkkarma.
He talked about parallax lambana, or dikatiji, that apparent shift in an object's position because we're looking from the edge, not the center of the Earth.
More noticeable for the moon being much closer than the stars or even the sun.
Exactly. And he revisited horizon dip, Dikchaya, how the horizon appears slightly lower than expected because of the Earth's curvature and atmospheric refraction.
Which affects rising and setting times.
And he included other refinements too: longitude corrections, Dṛkkarma, and Dṛkkarma, to make the calculated positions match the observed ones as closely as possible.
This focus on corrections is really the mark of careful science, isn't it? It shows he understood the limitations of a simple model and was striving for accuracy. Parallax correction demonstrates a really sophisticated understanding of the geometry involved. It's not just theory, it's about making the theory match reality.
It's this whole meticulous structure: the spinning spherical Earth, the coordinate systems, the trig, the corrections, that leads us to the crowning achievement of the Golapāda.
Eclipse prediction.
Yes. This is where it all pays off. We hit that pivotal moment, Gola, verse 37, where Aryabhata just cuts through centuries of myth. No demons, no supernatural causes.
Just shadows. Chayo is tama, shadow is darkness. Simple, profound.
He stated it clearly. A solar eclipse happens when the moon, Shasha, comes between the sun, Surya, and us, casting its shadow on Earth.
Moon blocks the sun.
And the lunar eclipse. That's when the moon passes into the Earth's own shadow, the Bhuchaya.
Earth blocks the sunlight reaching the moon.
It's purely geometric, physical. He explicitly rejected the Rāhu myth, the idea of a demon swallowing the sun or moon. This was revolutionary. It turned eclipses from terrifying omens into predictable, understandable, natural events.
It's hard to overstate the significance of that shift. Moving from myth to mechanics to a rational physical explanation, it fundamentally changed how people could view these spectacular events. It empowered understanding over fear.
And having established why eclipses happen, he then showed how to predict them in detail. First, the conditions.
Right, it's not every new moon or full moon.
No, you need the right phase, new moon for solar, full moon for lunar, and the sun, earth, and moon have to be aligned not just in a line, but also close to the lunar nodes, the pada, those points where the moon's tilted orbit crosses the Earth's orbital plane.
So alignment in 3 dimensions is crucial.
Exactly. Then he gets into the calculations, how to figure out the size and shape of Earth's shadow cone out in space, its length, and crucially, how wide it is where the moon passes through it.
Geometry again.
Pure geometry. And then using that, how to calculate the duration of the eclipse and its magnitude, the Grāsa, how much of the sun or moon gets covered. He used concepts like effective radii for the sun, moon, and shadow.
Sthityardha and Vimardārdha.
And applied the Pythagorean theorem to figure out the timing of contacts and the maximum obscuration. It's mathematically quite sophisticated.
Absolutely. Using Pythagoras to model the passage of the moon through the shadow or across the sun's disk is brilliant. It turns the event into a solvable geometry problem.
And he didn't just care about the numbers. He cared about what it looked like. He explained how to calculate the orientation, the Valana, basically, which part of the sun or moon gets covered first, how the shadow moves across, essential for drawing accurate diagrams, the Graha Paraleka.
So observers would know where to look in the disk.
And perhaps most impressively, his description of the colors of a lunar eclipse. He nailed the sequence. Starting pale, smoky, Dhūmra, getting darker, maybe a bit brownish or tawny, Kapila, and then that characteristic deep coppery red, Sakṛṣṇatāmra, during totality.
Which is remarkably accurate. We now know that reddish color comes from sunlight filtering and bending through Earth's atmosphere. Essentially, all the world's sunrises and sunsets projected onto the moon.
For him to observe and record that sequence so precisely is just stunning observational skill. He even noted practical things like how much of the sun needs to be covered before the eclipse is easily noticeable to the naked eye.
The whole eclipse section is just a masterpiece. Theory, geometry, calculation, observation, all woven together. It's the ultimate test of his entire cosmological system. If you can predict eclipses accurately, your model must be pretty good.
And as we've seen throughout this whole exploration, these ideas aren't just historical footnotes, they're alive. The basic concept of the celestial sphere, coordinates like declination and right ascension, that's still how astronomers map the sky, how telescopes point.
The fundamentals persist.
His spherical rotating Earth. That's fundamental to GPS. You literally cannot calculate your position accurately without accounting for Earth's shape and spin. Space mission planning depends entirely on it.
Couldn't send a probe to Mars without it.
Latitude, longitude, time zones, they underpin all global navigation, communication, travel, everything. The geometric methods, the trigonometry he used for measurement, that's the bedrock of celestial mechanics.
It evolved, of course, but the principles started there.
Even the observational corrections, like parallax. High-precision astronomy today relies on incredibly accurate parallax measurements to determine distances to stars. Calculating spacecraft trajectories requires accounting for it.
Tiny effects matter when you're aiming for distant targets.
And the eclipse theory. His shadow-based explanation and the geometric calculations are the direct ancestors of the complex software NASA and others use today to predict eclipses down to the second. It's used for planning scientific observations during eclipses, and even for missions where spacecraft pass into shadows.
The ancient code is still running, in a sense, inside our modern algorithms. It really underscores the lasting power of getting the fundamental geometry and physics right.
It's humbling, isn't it, to see how these ideas worked out 1,500 years ago are still so relevant, embedded in the technology we use every day.
It truly is. It shows that Aryabhata wasn't just solving contemporary problems. He was laying down foundational principles.
Which brings us, as we close this deep dive, to Aryabhata's own final thoughts in the Golapāda. His last couple of verses are quite profound, aren't they?
They really are. They offer a glimpse into his philosophy of knowledge.
He writes, and this is a translation, of course, "From the ocean of true and false knowledge, by the grace of Brahma, this supreme jewel of true knowledge, which was submerged, has been rescued by me using the boat of my own intellect."
Wow. The ocean of true and false knowledge. That's quite a statement.
It shows he was aware that not everything believed or written down was reliable. There's a need for discernment, for critical thinking, to separate the true from the false.
And the grace of Brahma may be acknowledging inspiration, or perhaps the underlying order of the universe itself.
Could be. But the crucial phrase for me is using the boat of my own intellect, Svamatināvā. He's emphasizing his own reason, his own logical effort, as the tool he used to recover this jewel of truth.
That's a powerful claim for the role of individual reason in science. It's not just about receiving wisdom, it's about actively working it out yourself, using your mind as the vessel.
It feels incredibly modern, that emphasis on intellect and reason as the pathway to knowledge.
It really does. It resonates with the core principles of scientific inquiry across the ages.
And then his very last verse, he names the work Aryabhatiya. He claims it aligns with self-existent reality, Svayavada, and declares it always true, Sadasatyam.
A strong statement of confidence in his system.
But then comes a warning. He warns against creating any counterfeit or distortion, Pratikañcukaṃ, saying it leads to the loss of merit and lifespan, Sukhatayupanshad.
That's fascinating. It's an ethical charge, isn't it? A responsibility that comes with knowledge.
Exactly, he's saying, this knowledge is important, it reflects reality, so preserve it accurately. Don't twist it, don't corrupt it. There's an ethical imperative to transmit knowledge faithfully.
Especially scientific knowledge, which builds upon itself. Distortions can lead inquiry down wrong paths for centuries.
So the Golapāda isn't just an astronomy text, it's the culmination of a whole scientific philosophy. Observation, math, rational thought, building a coherent model, predicting phenomena, and even reflecting on the nature of knowledge itself and the ethics of sharing it.
A truly unified vision from the mechanics of the cosmos down to the responsibility of the scientist.
It's been quite a journey, hasn't it? Through this ancient genius, this cosmic blueprint from 5th century India. Seeing how these ideas still echo, still inform our world, it really drives home the power of the human mind to figure things out, to build these incredible models of reality.
One sphere, one calculation at a time, as you said.
Well, thank you for joining us on this extended exploration, this deep dive through the Aryabhata, and especially its concluding chapter, the Golapāda, this season on Ancient Code, Modern Mind. This brings our detailed look at this specific text to a close.
It's been a privilege to discuss it.
And a real honor to share this ancient wisdom with all of you listening. Until our paths cross again on some future exploration, Harsh Raim, signing off.